Hello everyone, thanks for joining us today. My name is Nitin. I'm part of the scientific research group at Buddy.ai. This work was done in collaboration with Indian Institute of Technology, Madras. So, our work deals with an important question. Is it hard to learn a classifier on this dataset? This is a simple and fundamental question every data scientist faces in his day-to-day work. This is a very important question in an industrial setting. If we were able to gauge the difficulty of the problem beforehand, it might help us in various stages of a project pipeline, such as time allocation, resource planning, etc. In this work, we propose a method with which we can answer this question. So, let's get started. This presentation is structured into 5 parts. In the first part, we brush through some basic concepts that are necessary to understand our approach. In the next part, we introduce our approach for the problem. Next, we try to demonstrate our experimental setup and their parameters. After that, we discuss the results of the experiments conducted. At last, we close with some concluding remarks and future works. Let us cover some basic concepts that are necessary for us to understand the problem in hand. First, classification complexity. Identifying how hard it is to achieve a good classification performance over a given dataset can be useful in many ways. The phrases how hard it is to classify is what the term classification complexity means. In other words, classification complexity denotes the difficulty of learning a classifier on a given dataset. Determining the classification complexity of a dataset can help us solve the classification problem more effectively. It can help us in finding an appropriate classifier. It can help us in feature engineering. It can help us understand more about the nature of the dataset in hand. Now, let us understand what are clustering indices. Clustering indices are evaluation metrics that are used to measure the performance of a clustering algorithm over a given dataset. They are a direct indicator of different properties of the dataset over which the clusters were formed. They can tell us how sparse our data is distributed. They can tell us how inherently well separable our data is, and many more. Now, as we are familiar with the concepts of classification complexity and clustering indices, let us take a look at our approach. The intuition behind our approach is pretty straightforward. As mentioned earlier, clustering indices reflect different properties of a dataset. We believe that using clustering indices as meta features of a dataset, we can determine the classification complexity. More formally, we hypothesize that the clustering indices of a dataset has a strong relationship with its classification complexity. The three main contributions from this work are: 1. A novel method to estimate classification complexity of a dataset using its clustering indices. 2. A fully automated machine learning system which predicts the classification complexity of a dataset. 3. A clustering-based approach to extract meta features of a dataset. As we have established our hypothesis, now let us try to frame our problem more formally. First, how are we going to measure classification complexity? We measure classification complexity of a dataset in terms of hard or easy. Now, naturally, the second question is, when should we consider a dataset to be hard? We consider a dataset to be hard if and only if none of the classifiers that we tried to learn on it were able to score a classification performance of more than 60%. Now, the formal definition of our problem is: when given a binary class dataset D, our aim is to determine if D is a hard dataset to classify or not. Since we are going to use cluster indices as a meta features for our datasets, let us define I to be a set of clustering indices. Let "f" be the set of functions that transform a dataset D to a clustering indices I using a clustering algorithm. The image below depicts the transformation of the dataset into clustering indices. Also, let Q be an indicator function that determines if a dataset is hard or easy to classify. The function Q determines if the dataset is hard over a given set of classifiers, meaning it checks whether if at least one among the set of classification algorithms that was tried over the dataset was able to score a classification performance of greater than 60. We frame our hypothesis as a classification problem. We try to determine if a dataset is hard to classify or not using a classification complexity predictor. Here, the predictor is a mapping between the clustering indices of a dataset and its classification complexity. More formally, this classification complexity predictor is a mapping from clustering indices I to the classification complexity indicated in terms of hard or easy. Now, to train our predictor, we need a lot of data points. The inputs for our predictor are the clustering indices of a dataset, and the output is the classification complexity represented in terms of hard or easy. We compute clustering indices feature vector for every dataset. We might need a lot of datasets to create a training set of reasonable size for our predictor to learn. Here, the number of data points we can extract is bound based on the number of datasets we are able to collect. To overcome this, we split our dataset into random subsamples. We extract the clustering indices for each subsample of the dataset rather than the dataset as a whole. Other than giving the ability to create more data points, the random subsampling method also helps us in get more variance in our data points. Moving on to our next part in the presentation. In this part, we take an in-depth look at our fully automated classification complexity prediction system. The entire architecture is divided into two pipelines, the training pipeline and the testing pipeline. The training pipeline. In this pipeline, we try to train our classification complexity predictor. This pipeline has three phases. They are: first, the pre-processing phase. In this phase, every dataset goes through standard cleaning procedures. Also, in this phase, we split down a dataset into smaller subsamples using random subsampling method. Next is the data construction phase. In this phase, we try to extract cluster indices for every subsample using different clustering algorithms. Parallelly, we also determine the classification complexity label for each subsample using the F1 score obtained after training different classifiers on them. Next is the mapping phase, where we try different classification algorithms that can map the clustering indices to the classification complexity label of the subsamples. Based on the scores of Crayfold cross-validation, we choose the best classifier among the classifiers tried as our classification complexity predictor. Moving on to the testing pipeline, here we try to determine the classification complexity label for an unknown test dataset. This test dataset undergoes the same standard pre-processing procedures, and clustering indices are extracted from this dataset. These indices are passed on as input to our classification complexity predictor, which was obtained from the training pipeline. The predictor estimates a complexity label for this unknown test dataset. Next is the experiments and results section. For experimental purposes, we have chosen 60 binary class datasets collected from various public sources. As discussed earlier, we consider a dataset to be hard if and only if none among the set of classifiers that we tried to learn over the dataset was able to score a good classification performance. Now we choose 6 classifiers from literature as our set of classifiers, each one representing different modeling assumptions and parameters. Likewise, we also choose 4 different clustering algorithms from 4 different families. Since these clustering algorithms are from different families, their clustering results might vary accordingly, which will be reflected in the indices. The image below represents how a dataset will be represented as a clustering index feature vector. We have collected 40 clustering indices from literature, and We use the weighted F1 score as our classification performance metric. Moving on to our results section, first we try to validate our classification complexity predictor using a cross-validation. From the table, it is clear that the XGBoost classifier is effective with more than 90% correctness overall. This also validates our hypothesis. To validate the complete system, we do six-fold cross-validation over 60 datasets. We repeat this six-fold validation six times to ensure every dataset is used for testing. From the table, we can observe that on an average, 9 out of 10 times our system's predictions were right. We further extracted the important cluster indices that influence the complexity of a dataset. We used different correlation metrics to determine the direction of influence for these critical clustering indices. Now, to conclude, with results from our experiments, we successfully demonstrated our hypothesis that the clustering indices indeed have a strong relationship with the dataset's classification complexity. Also, our classification complexity prediction system was effective 9 out of 10 times on an average. Now, for future work, we can try to give explainability of the predicted complexity using the critical clustering indices. Also, we can extend our framework for multi-class datasets or by adding more clustering and classification algorithms. The code for our system is available in GitHub. We encourage you to try our system before you start solving your next classification problem. Once again, thank you all for your time and patience.